diagonalization and discussing diagonal matrices a bit. So some of this will be a little bit higher level, including an application coming from differential equations, which of course not all of you have had, but some of you are in it now, and some of you will take it in the future. And I'll have to keep things at a pretty vague level of detail concerning applications, but mathematically I can at least give you this this idea and sort of indicate what types of things I'm going to ask you to do in the future. Which reminds me, I do need to assign a new homework, which I will do. I'll try to do today. Okay, so I'm going to write the diagonal matrix this way. This is just saying AJJ, j equals 1 to n, just indicating that the row and column indices are the same. And if it's an n by n matrix, that means that you have a 1, 1 entry, a 2, 2 entry, a 3, 3 entry. This is bad notation because it doesn't say what's happening off of the diagonal. So later on down here, I adjusted it to use this word diag, which is a little bit more standard. And this is just indicating that off of the diagonal, you have zeros. So up here, I'm just telling you what a diagonal matrix is. Again, you've seen this before. So main diagonal, it's an n by n matrix. So you have you have potentially non-zero entries along the diagonal. Now, one thing to be clear, if I make one of these 0 and I keep these big zeros here, so all this notation means zeros above and below the diagonal, you are allowed to have zeros on the diagonal. And in particular, the matrix which is entirely 0 is diagonal as well, because the idea is the only place where you're allowed to have non-zero entries is on the diagonal. However, you are allowed to have 0 entries on the diagonal if you want. And I'll just remind you a couple things about diagonal matrices that are very, very useful. So first is that the determinant of a diagonal matrix is just the product of the diagonal entries. And you can check this, but this just follows from the definition of the determinant. So the idea being here that if you have a diagonal matrix, the only way it's invertible is if all of its diagonal entries are non-zero. And since these are the only entries, you just go down the list and you just see if there's a 0. If there's a 0, it's not invertible. If there's a 0, it is invertible. If there's not a 0, then it is invertible, because if the determinant is just this product, the only way to make a product 0 is if one of the constituent items is 0. So I just wrote here, invertibility is easy to check using the determinant. And in general, the product of diagonal matrices is very, very well behaved. So in general, we know, and this is a big thing for the upcoming quiz and final, that in general, matrices do not commute. Matrix multiplication is not commutative. So you can find matrices for which it is true, but in general, it is not true that DE equals ED. However, for diagonal matrices, in fact, it is. And you can see this is a very, very simple proof. When you multiply diagonal matrices, you just multiply their entries. So what I wrote down here is DE or ED doesn't matter when you multiply them. So one diagonal matrix is the A's, one diagonal matrix is the B's. Then the resulting matrix is just the product on the diagonal. So you just literally multiply the 1, 1 elements and the 2, 2 elements and the 3, 3 elements, and then you place those objects back in the 1, 1, 2, 2, and 3, 3. And since you do that, and you're looking at AJJ, BJJ, for instance, these are just scalars and they commute. So that means you can see immediately that ED and DE are the same, because AJJ, BJJ is the same as BJJ, AJJ. So I just wanted to emphasize that working with diagonal matrices is nice. They're friendly. Okay, so let's see what happens here. If we want to take a diagonal matrix and raise it to the kth power, remember all that means is just multiply it by itself k times. And of course for matrices, at least for the time being, we're thinking of k as being a natural number. So if k is 0 and you raise a matrix to the 0th power, what you get is the identity, for the same reason that when you raise any number to the 0th power, you get 1. So the same thing's going here. But once you have that, if you have d to the first, we know what that means. D to the second, d squared is just d times d, so on and so forth. But using this rule up here, if you multiply d times d, you just get ajj squared. And so similarly, if you have a kth power of matrix, then you're just raising the entry along the diagonal to the kth power. So again, I should have written the word diag here, just to let you know that d to the k is take the entry a11 and then raise it to the kth power. If you're taking d to the k, it's just a11 to the k, a22 to the k, a33 to the k, and that follows from this rule. Okay, so if we can define powers of a matrix like this, then you can hopefully, if you remember from Calc 2, you can define the exponential of a matrix. And this is a little bit odd, but just bear with me for a second. So the definition of the exponential function, going back again to Calc 2, is this power series expansion starting, and this should start at 0. I apologize. This index here should be a 0. So you take the infinite series of the matrix, the argument, to the ith power divided by I factorial. And the factorial definition is just multiplying, this might multiply like I times I minus 1 times I minus 2. So again, if you haven't seen this in a while, just go back to your Calc 2 notes. But the point is, to make this definition make sense, all we need to know is how to raise the argument to the various powers, which are 0, 1, 2, 3, 4, so on and so forth. So since we know how to compute d to the k, we know how to compute d to the I, and I here is just an index, it's not the imaginary unit, which means that the definition of the exponential makes sense. And I'll talk about later on why that is useful. So if you have a diagonal matrix and you want to compute its exponential, then what you do is you just multiply this out, and you can see that, and this takes a little bit of thinking, and maybe you want to do this with a 2 by 2 matrix, you have these series on each of the elements of the diagonal, but this right here is just e to the a11, this right here is just e to the a22, and so what you end up with is a diagonal matrix of the exponential of each of the elements. So it's kind of interesting because, again, if you start with a diagonal matrix and you raise it to the kth power, all you do is you just put the k power on each of the diagonal elements. So d to the k is a11 to the k, a22 to the k, so on. And if you do e to the d, that is the same thing as just exponentiating this, 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 and this, and creating the resulting diagonal matrix. So I will caution you, this property does not hold in general for matrices that are not diagonal. Computing the matrix exponential for matrices which are not diagonal will result in a matrix which is a diagonal exponential. So this is the result that we're going to use later on. Okay, cool. So now I want to talk about why, that was just sort of a reminder about why diagonal matrices are useful or are friendly. So now let's talk about why iterations and self-mappings are important. So in mathematical modeling, whether you're talking about discrete systems or time-dependent systems, continuous time-dependent systems, you often have something like this where you have a current state. So I said yn is the current state. So yn minus 1, for instance, would be the previous state. And you have a rule, and the rule tells you how to get from your previous state to the current state. And in the language of differential equations, which we're going to talk about in a minute, you know where you are now, and you're trying to compute the rate of change or the direction of change for your system. So if you know where you are, you use this matrix, which is, you can think of as a rule or a law, which tells you how to evolve in time. And again, if you haven't done calculus in a while, that's okay. I'm going to show you some ODEs here at the end. And if you're interested in iteration, so if you're thinking about an algorithm, you could have an initial guess, you apply a rule, and that produces y1. And after you've produced y1 from y0 using this rule, then you can apply the rule again, and that will give you from y1, y2. But if you do this iteratively or inductively, then when you apply a to y1, that's a y0, which is just a squared y0. So in general, if you want to apply k powers of a to the initial condition, that will tell you your kth state as you iterate the operation or the rule a. So again, what I'm doing here is I'm just applying a once, and then again, and then again, and then again, and again, and I can go up to the kth time. So in mathematical modeling, it is often the case that you have to deal with powers of applying a matrix. So you have some state, which is a vector, you have a matrix, and you need to apply it several times. And so I just wrote here dynamics. This is things like dynamical systems, math modeling in biology, math modeling in mechanics, search engines, right? The search engines use this sort of iterative approach, and they also use eigeninformation, which will come up a little bit later in this discussion, and just algorithms in general. You may have something where you need to iterate, and when you iterate a rule, you will always get something that sort of resembles like this. So I've basically just described a huge chunk of application in mathematics, albeit at a sort of high and vague level, but the point is that things like this are useful. So The point is, if I want to compute a to the k, why not? So compute this matrix and then apply it to a vector. We know from the previous part of this discussion that if it's diagonal, then everything is good. There's no worries. But what about when it isn't diagonal? And this is where the diagonalizability of a matrix comes in. So remember from our previous video, not all matrices are diagonalizable, but if they are, then they can be written in this way. And so the idea is that even though A itself may not be a diagonal matrix, it can be expressed as a diagonal matrix with this conjugacy of this other matrix P. Remember, D corresponds to the eigenvalues and P corresponds to the eigenvectors in a particular way. So even though computing diagonal matrix to the K is very, very easy, right? So that was like here, d to the k gives us the diagonal entries with the kth power. When we have a diagonalizable matrix, we can get away with something which is almost as nice. So if we check this out, a to the k for a diagonalizable matrix is just p d p inverse to the k. We're going to use properties of matrix multiplication here. So just write the matrix k times 2, and then I use associativity of matrix multiplication, meaning I can't rearrange things, but I can group them using different sets of parentheses. So I notice there's a P inverse here and a P here, so those will cancel, right? And then that'll put a D next to a D. But then there's a P inverse here and a P here, those will cancel, and that'll put another D here. And if I continue through this procedure, what I'll end up with is P d to the k P inverse. And so that's telling you that if A is diagonalizable, then so is a to the k, because this is a diagonal matrix. If D is diagonal, d to the k is diagonal, and then I'm conjugating by the same P and P inverse. So the beauty of this is that if I want to compute easily high powers of k, I wouldn't do this by simply performing matrix multiplication k times. That's very cumbersome and slow. If I express A through its diagonalization, this object here, then I can compute a to the k in a very simple way using 3 matrix multiplications. D to the k is easy. You simply take the kth power of all the entries on the diagonal, and then you just apply P and P inverse. So you get away with 3 matrix multiplications, really 2, rather than k. And so if k is 10 million, and you have to iterate this 10 million times, then d to the k is very simple to compute, and you end up only having to do 3 calculations. So you're sort of gaining speed in this calculation, and you're able to do it in a straightforward way. Similarly, if you want to compute the matrix exponential of a diagonal matrix, so take A, expand it in this way, and then you just use this argument in the power series definition, which I gave before. And so when you write out what this is, and then you use this property, what you see is in the same way that a to the k is p d to the k p inverse, e to the a, so I'm applying a different function where a is the argument, the exponential, is just p e to the a p inverse. Sorry, not e to the a, e to the d, where d is the diagonal part. So this formula is also very useful, because if you need to compute the matrix exponential for a complicated matrix and it is diagonalizable, then write it in its diagonal form. And again, instead of having to do something crazy with a power series, now what you're doing is you're just taking the diagonal matrix, computing the exponential of its diagonal entries. Okay, so e to the d, that's easy to do. It takes you 5 seconds to look at the diagonal and then plug them into the exponential, and then you do 2 additional matrix multiplications. So in the next and final video, I'm going to talk specifically about why this is useful. In particular, we're going to talk about some ODEs.